All right, welcome to our presentation. We're going to be talking about our model, which performs zero-shot learning for geolocalization in restricted image domains. As an introduction, the problem we wanted to solve was being able to predict the location, geographic location, from an input image. We can imagine various situations where this would be relevant, such as law enforcement, if they're trying to find a criminal or a missing person, being able to use images in the investigation and predict where they were taken, as well as social media functionalities like being able to tag an image by its location automatically using this kind of model, as well as several other opportunities. The contributions that we'll focus on. One was the implementation of OpenAI's CLIP model to assist in the increasing the accuracy of our model, as well as expanding the data set. So the previous works that we built upon, the first one was called GeoGuessr LSTM, which attempted to do something similar using the data from the United States, being able to predict, split the United States into a grid, being able to predict the specific cell where the image came from as a classification. The second work that we based on, learning generalized zero-shot learners for open domain image geolocalization, that provided us information and inspiration on how to use CLIP as part of our model, though our model is in a specific domain instead of open domain.
So our first contribution, we basically wanted to expand on the data set. So the data set used by the original project that we took inspiration from started with splitting the US into 243 grids, kind of like you see the grids below for the UK, finding 40 random locations per grid with 3 images per location for a total of around 29,000 images. So we started out doing the same thing with the US, except only doing 20 random locations per grid. And then on top of that, we appended images from the top 100 cities in the US by population to get us a total of 20,500 images from the US. And then as well as that, we added imagery from the UK, as that was what we were going to mainly train our models on. And the reason we chose images from the UK is because the UK had a lot of street view data, similarly to the US. And so for the UK, we started out splitting the UK into 246 grids, finding 20 locations per grid with 3 images per location. Then we basically found over 150 cities in the UK, and we found image data based on those cities for a total of 97,260 images from the UK. Next slide. And so here's an example of some of the image data we found basically by scraping from Google Street View API. And so this is an image from Hermitage. And so our image locations basically started with an image from 0 degrees, an image from 90 degrees, and an image from 180 degrees.
Our next contribution is using OpenAI's CLIP model, which is a zero-shot image learning model. Essentially, using CLIP, we can give each image in our data set a label, which corresponds to the location of that image. And CLIP can learn the relationship between the text and image embeddings simultaneously. So using this, we can pre-train CLIP's model with our data and with our encoded text embeddings. And after a few epochs of learning, theoretically, we should be able to pre-train a model to get very good at distinguishing between our data. Our methodology is briefly outlined here. So we start with the data loaders. In PyTorch, you need to load the data, and due to the complexity of our data sets and the way that we segment them into folders with coordinates, this ended up being quite an interesting task. Furthermore, we need to encode both the image and the text into an embedding. We use ResNet50 to encode images and Distilbert to encode the text. Finally, we can use the CLIP model to pre-train and take the images and get some interesting data from them. We outline more in detail in the next slide. First, our 2 data sets are UK CLIP and UK Cities CLIP. UK CLIP being the grid-based data collection that we originally had. The folders in our Google Drive were split into grids, and each grid having 20 different folders. Each folder corresponded to a coordinate pair, and each coordinate pair folder had 3 images inside of it, corresponding to a panorama of that location. Then our other data set was the UK cities clip, which was much simpler, just based off of cities, and each city having its own different set of images, each one having 600 in the case of top 50, and in the case of top 150, the top 50 had 600, next 50 had 100, next 50 had 50. Data processing, like I said, we image and text encode both with ResNet 50 and Distilbert, and we use a projection head neural network, which is a linear neural network with batch normalization and residual connections that takes the images and text and projects them to the same dimension space, being 256 as specified in the clip paper. Finally, we can train the model. We use a train test val split 70-20-10. We use the validation set to tune the hyperparameters, and we use a standard cross entropy loss function as set in the OpenAI clip paper. And we use many of the same hyperparameters as specified in the paper. And we evaluated in particular, we evaluated the epoch through a few different tests, running the model a few times, finding that 6 epochs was actually the ideal number of epochs. And we will talk about that further in the presentation.
So here are the results from our basically accomplishments. We found 117,840 images with accurate location labels gathered across the UK and US, including city name and coordinates. And then from this larger data set, we grabbed 3 smaller data sets for training, which was the UK grid data set, which was images across the UK that we split into a set of grids, which was around 15,000 images. And then a data set of the top 150 most populous UK cities, which had around 52,500 images, and a data set of the top 50 most populous UK cities, which had around 30,000 images. And so for our first model, the grid data set, this was our worst performing model, which had a test accuracy of 2.28% and an average distance from predicted and actual location of 292 kilometers. And part of the reason this was our worst performing model was the fact that each grid location only had 60 images. So there was not a lot to basically train on. And so here in these 2 graphics, we can see basically the loss versus the number of epochs for our training and validation sets, as well as the percent of images within these 3 distances. And then the image below basically shows 5 examples of predicted grid versus actual grid for these 5 images. And we see here in this example that none of them were labeled correctly. So for our second model of the top 150 cities, it performed much better than our first model with a test accuracy of 14.34% and an average distance of 128 kilometers. And we see in our example images here that this model is doing much better at classifying these images. And then the final model of top 50 cities was the best performing model at test accuracy with 27.08% test accuracy, and it did slightly worse, but pretty much the same as the last model in terms of average distance from predicted to actual locations.
All right, so now in order to compare with our models with the GeoGuessr LSTM, the first work that we cited earlier, they said in their own report that it wasn't a particularly accurate model. Their average distance, so even though we use different land masses that we're training on, we thought that a good way to compare them was to consider the average distance between the predicted location and the actual location. So in their model, their average distance was 1,931 kilometers. And if you consider the radius that sweeps out, that's a pretty significant portion of the United States. So it's fairly weak relative to that particular landmass. However, if you consider ours on the right, relative to the United Kingdom, although our grid model wasn't particularly strong, the 50 and 150 cities data sets provided radii that were actually fairly small relative to the United Kingdom with numbers that we provided earlier. So finally, as a conclusion, it's important to consider the ethics of these models and of this type of these types of models, because if someone posts something online, they may want to keep private where exactly they are, especially maybe a celebrity. They don't want to necessarily broadcast where they are in the world. So it's important to consider the danger of these models. Another thing to consider is that although our model was specifically tuned to the United Kingdom, we think that it's fairly extrapolatable to other countries, provided you have enough sufficient data. And lastly, in terms of considering how such models could be improved in the future, perhaps we could take strategies from human geoguesser experts, like you see on the right, who use various different details in order to train themselves to get good at guessing where in the world an image is found, and maybe implementing explicitly some of these tricks and strategies they use into a model might help improve it and give it a leg up. Thank you very much.